We are going to consider our last and final test. We are on page 169, section 4.7, the ratio test. I will admit, this is probably my favorite test when I was in Calc 2 as a student because it felt like the most straightforward and the easiest to use. So let's talk about it. Let's talk about this test for a minute and when it's useful. Right? So this is our ratio test. Essentially, we are going to be looking at an infinite series. Suppose we take the limit of these two terms. This is the first term, this is the term before it, and we determine the limit, some number r. If that value is between 0 and 1, including 0 but not including 1, then our series converges. Remember, when we find this limit r, this is not what our series converges to. This just confirms that the series converges. Or if that value is bigger than 1, then it diverges. If it is equal to 1, unfortunately, the test is in fact inconclusive. And so you will have to use another test. Right? So where is this useful? Right? A couple of places this particular test is useful that I like to be aware of. It's useful for factorials. Remember, our factorials were like 2 factorial, n factorial. This is where we're going to find it useful. Another place that they are useful is when we have an expression raising to a power of n. Like 2 to the n, like we see down here. Essentially, we see, hey, this is not geometric, right? Because we've got this n value right here. If there were two tests that I commonly tried first, it was ratio test. As soon as I saw that exponent, as soon as I saw a factorial, or I would jump straight into the divergence test. But with both of those, right, we have some inconclusive tests. And then if neither of those work, then I would jump into another test because they require a little bit more work. Assuming that we're not looking at something as geometric. If you have something that's geometric, stick with that, right? That one's the easiest. It's just the being able to identify it. So let's practice using this. We're not going to talk necessarily about proofs here. And so let's jump down to this example. And so let's talk about this a sub n and this a sub n plus 1 that we needed in the definition, right? So our a sub n term is, in fact, this series right here. It's important to note that when the upper and lower bounds aren't written, we do assume that this is in fact an infinite series, and we know that the domain is all positive values, and so if it was bounded, it would have stated it, right? So our a sub n is n over 2 to the n. For our n plus 1, all we're going to do is take all our n values and add 1. So n plus 1 to n plus 1, right? And so for the ratio test, hopefully it works, right? We see this to the n power. And so what I'm going to do is I'm going to take the limit as n goes to infinity, absolute value. This is really useful for when you have like negatives, like a negative 2 to the n, stuff like that. Let's set it up though, right? So we want a to the n plus 1 over a sub n. So I'm going to plug in what I got. A to the n plus 1, n plus 1 over 2 to the n plus 1 divided by n over 2 to the n. Absolute value. I like to do my algebra rules with fractions where I keep the top, change this to multiplication, and then flip the bottom. Back when we learned about fractions. And this is where I hit a point where I look at it and I go, what can I simplify? What a lot of this is playing on algebra rules. Like one of the first ones that I kind of look at is the absolute value bars, right? I kind of analyze my functions and I'm like, do I really need these absolute value bars? Remember, n is all positive integers. So this is positive. This is definitely positive. These are exponentials. Exponentials are always positive, right? So in fact, since this is all positive, we don't need the absolute value bars. Don't need these absolute value bars. So what I'm going to do is the limit as n goes to infinity. Now I have this n plus 1 over 2 to the n plus 1 times 2 to the n over n. My personal preference is to get rid of any negative signs before I start applying any algebra rules. It just helps me kind of get situated. Now I can essentially simplify this as much as possible. So simplify first. So we're going to simplify. So I have the limit as n goes to infinity of n plus 1. And when I see these exponentials like 2 to the n, right, I think of my exponent rules. So 2 to the n plus 1 can be rewritten as 2 to the n times 2, right? Since 2 to the n times 2 to the first, right? There's that rule where when we multiply things that have the same base, we add their exponents. So the reason why this is nice is because now we can cancel out the exponentials, which is kind of the goal. Canceling out these exponentials, canceling out these factorials. This is why it's useful. And so now I have the limit as n goes to infinity of n plus 1 over 2 times n. Right? Don't forget that 2 down there. So we've been working a lot with these. This is in fact, so kind of looking at this is an infinity over infinity case. If you plug in infinity, you can kind of see, which means I am going to apply L'Hopital's rule to take this limit. So I'm going to take the derivative of the top, which is just 1, the derivative of the bottom, which is just 2, the limit of a constant is equal to that constant. Remember, this is our R value, right? So here we have R equal to a half. And this is where you jump back up to your test and you figure out like which case this is. So here's my R value. And we kind of look at, is it case A, B, or C? Since R is equal to a half is in fact between 0 and 1, right? So let's write that. So 0, 1/2 between 0 and 1. So it converges. We don't know to what, we just care that it converges. So our conclusion is that this series n over 2 to the n converges by the ratio test. Done. All right. Let's take a look at the next one together. Let's talk about these factorials a little bit. As soon as, oh, look, we see both of those. We see the factorial. We see the exponential. That is just a key indication of ratio test, right? So I always like to start by finding my a sub n, which is just 10 to the n factorial, a sub n plus 1, right? Where I'm just going to take all my n's and I'm going to add 1, even to the factorial. I do like to add some parentheses to this one just to be clear. Just kind of recall, it's been a while since we've talked about factorial. 5 factorial is the same as 5 times 4 times 3 times 2 times 1, right? What we do is we multiply all the terms after 5, or all the values after 5, and that 0 factorial is always equal to 1. So let's jump into this limit. I have the limit as n goes to infinity 10 to the n plus 1 over n plus 1 factorial divided by 10 to the n over n factorial. Limit as n goes to infinity. Again, we have another example of exponentials and factorials. N is always positive. We don't need absolute value bars anymore here. We're good. And so I'm going to consider that. I'm also going to rewrite this as 10 to the n plus 1 over n plus 1 factorial times, flip it, n factorial over 10 to the n. And in my next step, I'm going to simplify. How I'm going to do that, again, these exponentials, I'm going to rewrite 10 to the n plus 1 as 10 to the n times 10. For my factorials, what I'm going to do is I'm going to take advantage of this fact, right? Since n factorial is n times n minus 1 times n minus 2, right? All the values after n. What I like to do is I notice this is greater than 1. So I can rewrite this as my first term, n plus 1, whatever that is, times the second value right after that. This will allow me to cancel out the factorials because we don't really know how to take limits of those. And this is kind of the goal behind the ratio test, is it gets rid of these factorials. It gets rid of these exponentials. And now what we're left with is the limit as n goes to infinity of 10 over n plus 1. This is not a L'Hopital's rule case. I have 10 over something that's growing really big. That tends towards 0, right? There's our R value. This R value is in fact between 0 and 1, essentially equal to 0, right? So it converges by the ratio test. So I love these for exponentials. I love these for factorials. As soon as you see those, jump straight into it. I also really like them for when I see these negative values, these negative 2 to the n's. These absolute value bars are really going to take care of those really well, right? So if you'd like to also see this example, feel free to stick through it. I'm going to work through it pretty quickly, right? I'm going to jump straight into my limit as n goes to infinity. I am going to go ahead and do negative 2 to the n plus 1 over n plus 1 squared. I'm going to go ahead and just set it up as multiplication times n squared. I'm going to flip it to negative 2 to the n. Feel free to jump steps. If you have any questions, definitely shoot me a message. I got you. All right. I'm going to separate some things first. This 2 to the negative 2 to the n plus 1. I got negative 2 to the n times negative 2. I am going to expand out that n plus 1 squared, n squared plus 2n plus 1 using what I know about formulas. I've done it a million times. You can always multiply it off to the side. Right? N squared negative 2 to the n. I can cancel out these negative 2 to the n. Sorry. I have a cat that's trying to claw its way into this room. It's very distracting. I can cancel out those, right? Limit as n goes to infinity. What I'm actually going to do is I'm going to write it as the absolute value of negative 2 to the n squared. Multiply the tops here and here. N squared plus 2 to the n plus 1. And in this step, I'm going to get rid of my absolute value bars, right? The only negative value that we have here is this negative 2. Remember, with limits, we can pull constants out. We could do stuff like this. I'm getting rid of the negative value. I'm taking the absolute value of 2. I have limit as n goes to infinity. n squared over n squared plus 2n plus 1. And this is a L'Hopital's rule case. Again, right? This is our infinity over infinity case. Let's take our derivative. I get 2n over 2n plus 2. This is, in fact, another infinity over infinity case. If I plug in any, so I'm going to take another derivative. So I have the limit as n goes to infinity times 2, 2 over 2, which is a constant, 1, the limit of a constant, so I get 2 times 1, which is 2. And since 2 is bigger than 1, right, go back up to your test. If your R value is bigger than 1, then it diverges. So what we have found is that, therefore, this particular series, n squared, diverges by the ratio test.